Good morning, everyone. Welcome to Chemistry with Professor John. All right, we are discussing alkenes today, and we will start out with structure, naming, stability, and maybe some synthesis reactions. Okay, and that should be a review of what we did last time. I'm talking about elimination reactions. Okay, alkenes. Okay, so the key concept and skill that we like to get out from this topics are be able to draw and name alkenes, okay, with given molecular formulas, meaning how many carbon, hydrogens, and so on and so forth. If you remember cis-strand system, we're going to be looking at alternative system known as E and Z as well. And then we'll look at the stability of alkenes based on structure and stereochemistry. Okay, now alkene is alkane. You take away two hydrogens and at least two hydrogens per double bonds. Okay, two hydrogen per double bonds. So it's got carbon-carbon double bond. The bond energy or bond strength is about 146 kilocal per mole. Notice the sigma bond is a little bit stronger than the pi bonds, 83 versus 63. So less stable pi bond means more reactive. Okay, so if anything happens, it's going to happen to the pi bond first before you break the sigma bond. Okay. Now, a single bond is sp3 carbon. If you look at the carbon-carbon single bond, the distance is the bond distance is 1.54 angstrom, and 10 angstrom is equal to 1 nanometer, or you can say 1 angstrom is 100 picometer. So you know it's really small. Now you compare with the sp2, that's shorter bond, shorter orbital. So the double bond is shorter, and that's about 1.33. And of course, if you next time we're looking at triple bond, but triple bond would be 1.2 angstrom, just to compare. Okay, now and that's because of the s orbital make the orbital shorter, therefore the bond is shorter. Okay, double bond consists of a sigma bond and a pi bond. Okay, half pi is on the top and half on the bottom. Now, pi bond is the result of parallel p orbital overlap. Sigma bond is the result of head-to-head overlap. All right, now let's talk about. Oh, I gotta mention. There is some restrictions in rotations about the carbon-carbon double bond. Just like if you hold something in your hand, or just one hand, so you got your arm is free to rotate because that's just one arm. But if you hold a racket or something, like to play tennis, you hold a racket with two hands, so that means you got double bond, and that's stronger, but it's harder to rotate. So there's some restriction in rotation there. Okay, now let's talk about elements of unsaturations, also known as degree of unsaturation. So you can call it EOU or DOU, okay, degree of unsaturations. Now, Okay, so 1 degree of unsaturation is a ring or a pi bond, meaning there's a decrease in 2 hydrogen atoms. Okay, so it's very simple. When you make extra bond, you have to remove 2 hydrogens to make the extra bond. So that's 1 degree of unsaturation. So all these molecules have 1. If you notice the formula for alkane, we're not talking about straight cyclic, just a straight alkane. It's CnH2n plus 2. So if you have C4, it will be H2 times 4 plus 2. We would have 10 hydrogens. But then notice here we have 8. Okay. So this is known as saturation hydrogens. So you take 10 minus 8 divided by 2, because 2 atoms makes a bond. You got 1 DOU. Okay. Now, what if a molecule has more than just carbon and hydrogens? So, like halogens, we can count that as hydrogens. Okay, because it has 1 bond. Now, oxygen has 2 valence, has 6 valence electron, in which there's 2 single valence electron, meaning it can make 2 bonds. So if you stick a oxygen somewhere in a molecule, it does not change anything. It does not change, degree of unsaturations. So you can ignore it, okay? Nitrogen has 3 bonds, so I think about it as 3, so it's missing 1. Carbon has 4 bonds, right? So carbon has 4. So nitrogen has 3, so it's missing 1. That's called like half valence as carbon. So it needs 1 more hydrogens. So when you take it away, you take a hydrogen away to accommodate, for the valence. Okay, for example, if we have C5, this is C5, H11N. All right. Now, if we're going to calculate degree of unsaturation, that would be, we take away C5H11N. If we take away NH, so we'll have C5H10. Now, if you look at the formula, C5H2 times 5 plus 2, that's C5H12. That's saturated. So we are 2 hydrogens short. You guys see it? So it's 12. So DOU will be 12 minus 10 divided by 2. So it's 1 DOU. And you can see here, knowing the DOU is important because that will help us to predict the structure. So either it has a ring or a double bond. Here we have C4H6NOCl. Okay, so nitrogen take away hydrogens. Oxygen we can take it off. Cl we can replace with hydrogens. And then nitrogen take away hydrogens. So we end up with C4H6. Well, C4, we're supposed to have H2 times 4, that's 8 plus 2 is 10. That's saturated. So it's 10 minus 6 divided by 2. We have 2 DOU, which makes sense. It's got a ring and it's got a double bond or two double bond. Okay, now is the fun part. So that's degree of unsaturation. That's kind of give us an idea what the structure would be like. You know, either a ring structure or double bond. Now, how about naming? You know, there's only one letter we have to change, which is the E instead of A. So if this is this, that's a 4 carbon, so it's a butane. So now we just have to change to butene. If you only have one carbon, I mean 2 carbon, that's just ethane become ethene or ethylene. That's a common name. If you have 3, it's always number 1. That's propene or propylene. Okay. Now, if you have 4, you have to number it because there's a possibility that double bond is not at number 1. Notice you only pay attention to the first carbon of the double bond. So that make it a 1-butene or butuene. That's a new method. Here it should be 1, 2, 3, 4, 5, 6. Now the rule also apply the closer to the first branch or the first functional group. That's also apply. So in this case, we don't want to go from right to left. That will make 1, 2, 3, 4. Okay. Hexene, that's not good. So we go from the left side because it's closer. So it's 2-hexene or hextuene. If you have 2 or more, it's no big deal. 2 mean di. So that's 1, 2, 3, 4. You only have to mention the first carbon of each double bond. So that's why it's 1,3-butadiene. Okay. There's also 1,2-butadiene. So that would be 1, 2, 3, 4. So that's 1,2-butadiene. 2 double bond back to back. And we have 1, 3, 5. 1, 3, and 5. Heptadiene because it has a total of 7 carbons. We also have cyclo, so it's cyclooctatetraene. Okay, it's all evenly distributed, so we don't have to number it. Here we go from left to right. So we got 6-methyl, 3-methyl, 3-methyl, 6-methyl, or 3,6-dimethyl, 2-heptine, or hep2i. Now notice the last one here on the right, you have to put number 1 on the double bond because that's a functional group. That's more important than the branch. So that's why we got 3-methyl 1-butene. Now we do have some interesting branches like methylene, which is a methyl losing the hydrogens. Vinyl, just put another carbon in, CH, and alu, that's another carbon. Okay, so and here's a few example. We got a branch like that. So if you have this, that would be just cyclohexane. But what if you have a double bond? You know, it's hard. So we're gonna call this one right here is a CH2. So we can call it a methylene, a methylene cyclohexane. That's the best way. Now, if we have this, then it's gonna be 1, 2, 3, 4, 5, 6. So we do have to number it because we have a double bond on the ring. Okay, so if you do 1, 2, 3, 4, 5, that's counterclockwise. That's good. If you start number 1 right here, that's not good. 2, 3, 4, 5. 6. Okay, so we don't want that. It's just the double bond end up at number 5 instead of number 4, so that's not good. So that's why 4-methylene cyclohexene. That's vinyl. So we got 1, 3, 4, 5, 6. That's why it's a 3-vinyl 1,5-hexadiene. Diene means 2 carbon. 2 double bond. Here's obviously, you can do 1, 2, 3. You can do 3 bromo. 1. Actually, it doesn't have to be 1. It's just propene. But that's no other way around it. Okay. And then you got 1, 3, 5. So you have to start 1, 2, 3, 4, 5, 6, 7. The double bond number has to be lower. So we cannot start at bromine. Okay. Now, I'm going to stop right there. In the next video, we're going to talk about the cis-strand easy stereochemistry stuff. Okay. Thank you, everyone.